As we saw for the one-way ANOVA, we will break up the variation of the responses into different components. And we're going to do this now for the two-way ANOVA. We're going to follow our textbook and describe this in terms of a fixed effect model. And what this means is that any observation in any cell in our table can be considered as generated by the following models. So the individual cell value for factor A at level I, factor B at level J, and a particular replicate K, can be considered an overall, it can be considered made up of an overall mean value where all the data is centered, plus a value called alpha sub I, which is the effect of factor A at level I. And then we have a beta value, which is the effect or the component to the measurement, which is caused by factor B being at level J. Now, we also have an interaction component, this alpha beta. So this is the interaction of factors A and B when they're at their respective levels I and J. And finally, this little error factor, which we assume is normally distributed and independent at each cell. And because obviously if you're setting a factor A and factor B at specific levels, every single one of the replicates should be the same. But it's not. We generally have some kind of error factor, and we need to then use this data to see if our effects due to factor A and B and the interaction are significant compared to that error. Now this is called a fixed effects model because the levels in the factors are assumed to be the only levels available. They're fixed levels. So in this model then, we can substitute the overall mean and the factor effects with estimates from the data. We've taken all this data, we need to use it. Now here I'm just going to make sure you can see, should have a hat over it here. And again, don't get too caught up in the dots and things, just we're getting the general idea. So the estimate for the overall mean, well, the best we have is if we take all the data that we have and average it all together, y bar dot 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 to all levels of A, all levels of B, and all different replicates. That's going to be our overall mean, and that's the estimate for this mu, the basis for our measurement. The estimate for the effect caused by level I of factor A is going to be called this alpha I. We're going to use the row averages, right? Because the row averages should be the same for factor A at a certain level. And so the row averages for factor A at a certain level, and we look at that as the difference between that and the overall average. So that's what we're going to use then for alpha I. Then we have this effect due to factor B. And again, we look at the column, this time the column average for every single B level minus the overall average. So that should make sense there. We also have more complicated equation, and don't look too closely at this. Here's our interaction of A and B, and we have it written out here. What this means is that the estimate of the effect caused by the interaction between factors A and B is going to be the remainder in the cell average after accounting for the overall mean and the factor effects. And finally, we have this error. Now again, in every cell, all of these values here should be the same for every single cell. So what we're going to do is take the cell average and subtract the individual average. And any difference there will give us this idea of the random error. Now again, don't get overwhelmed by all of this, all these dots and I's and K's and J's. What we're trying to do here is take measurement data, trying our best to estimate the effects of the two factors that we varied, and to separate out these effects from their interaction and from any random error. Remember, our goal is to see if our effects A and B are significant, and so we'll be comparing this then to the overall error. So one more tough slide, and I've skipped a lot of the details here, but what we're going to do is subtract the estimates that we have from our data into this equation. So this is the response, one individual response. Again, factor A at I, level I, factor B at level J, and the kth replicate. Going back a slide a second, here this mu value can be estimated by y bar dot dot dot. So here we have y bar dot dot dot. The alpha value can be estimated again. Here we have y bar I dot dot, so the overall row average minus the overall average. Beta was the column averages, look like that, etc., etc., etc. Now, if we do this, you plug all those in. So here we see and in this case, what we've done here is we've taken this y dot dot dot, we've subtracted it from here. So there's yijk. We've subtracted then the overall mu estimation. Here is our alpha I estimate. This was our mu estimate. Here is our beta estimate. All right? And then this was from the previous page, the alpha beta estimate. And finally, our error estimate that we've gotten. We plug all that in and we square both sides and sum over all the observations in all the cells. You get the sum of squares for each component. So it's the same thing we did for the one-way ANOVA. That was maybe easier to understand. Here we're showing how this comes from the fixed effects model, and here is the answer. The sum of squares total, so the overall sum of squares for everything, this was this yijk minus this estimate for the overall mean, this time squared, here's the squared, and summed over all the different possibilities, is equal to the sum of squares for factor A plus the sum of squares for factor B plus the AB interaction sum of squares plus the error sum of squares, which we write here as sum of squares total equals the sum of squares for factor A, it should be a big S here, plus the sum of squares for factor B, plus the sum of squares for the interaction AB, plus the sum of squares for the error. Now, each of these has each of these components, or let's say this, each of these estimates of the variability has a number of degrees of freedom equal to the number of independent squared terms that are summed. So for example, if we look at this SSE, this error term here, right? We have A times B, so we have for each of the, this is looking then at each single cell value. We have A levels of factor A and B levels of factor B. This gives us our metric, so A times B gives us our matrix, and then we have K replicates in each cell. So you would multiply that then by K to get the number of values in this entire term. But because we are using a cell average, excuse me, not K, N replicates in each cell. Because we're using this cell average, we have -1 independent value. We only have n-1. So the independent values in the cell are then n-1. And if you didn't follow that, it's okay. We give them to you here. You can look at that later. But what's important then, for example, the degrees of freedom for this error value is the number of independent values we use for calculating that. And here it's going to be AB times n-1. If you look at this again, now we're looking, the same data is all here. Here's the error we just looked at with AB n-1 as the degrees of freedom. Factor A, you've got A different levels, and we're using the overall mean. So we have to do A minus 1 for our degrees of freedom. Factor B has B minus 1 degrees of freedom. The interaction AB is A minus 1 times B minus 1, and then there's our total. So again, we've already calculated out our sum of squares term for factor A, for factor B, for the interaction, and for the error. And again, all given to you, your computer will do this, right? Now, what we learned was that we need the mean squares. And before, we just had the mean squares for one factor versus the error. This time, we're going to use for our F factor mean squares of A over mean square error. There's the mean square error. For factor B, it'll be mean square B over the mean square error. And for the interaction, it'll be the mean square AB over the mean square error. So the same procedure, but this time we do it 3 times instead of just 1 time, because we've got to look at both factors plus their interaction. Now again, the mean squares, this represents the standardized contributions of variability by the different sources. Standardized because we're taking this idea of variability, the sum of squares from the particular source, and we're dividing it by the degrees of freedom. So we're standardizing then for the source from each different source. The overall mean squared error then represents the variability in the data solely due to experimental error, variability from unexplained noise factors. And again, if the variability from a factor is much larger than the variability from the experimental error, then we can conclude that the factor is significant. So we take the ratio of the mean squares of each factor to the mean square error, and we see if this F factor is large. Now, as we talked about before, we have to use the F distribution with degrees of freedom φ1 and φ2. So I've got this all here. So φ1 and φ2 then are the degrees of freedom for the numerator and the denominator respectively. And again, what we'll do is look in tables where we're choosing tables for F alpha. For example, alpha equals 0.01 or 0.05 for 99 or 95% significance. So let's do our example and you'll see how simple this is. Back to our lawnmower, right? Now, what we've done here, we've taken exactly the same data you had before. We just put it in the ANOVA table. So here we have factor A, blade angle, and factor B, deck height. Factor A goes from 12 to 16. This was level 1, and this was level 2. Factor B, level 1 and level 2, 5 inches, 7 inches. Again, we have our cell averages, which we already calculated at the very beginning. We have our row averages and our column averages and our overall average. So going into our fixed effect model, and again, not expecting you to be doing this unless you want to prove to yourself that this works. And here I've given you actually the shortcut equations to make this a little easier. We would go in and calculate the sum of squares total, the sum of squares due to factor A, the sum of squares due to factor B, the sum of squares due to AB, and the sum of squares due to the error. So if you plug all these things in, you end up with the sum of squares total equal to 1,402. And here you can, if you want to check it, you can go and see the values. Here's sum of squares A, for example. We take our row factors, which are the shortcut equations. We get 2 for that, 242, 1152, and 6 overall. Let's look at this in the table form. So factor A, the sum of squares was 2. Degrees of freedom, remember it was A minus 1, or I have this over here, A minus 1. We have 2 levels for factor A, so it's 2 minus 1. The degrees of freedom for factor A is 1. For factor B, the sum of squares, if you calculate it out, was 242. We also have a degree of freedom equal to 1. For factor B, the interaction, Same as before, you also get a degrees of freedom equal to 1. And for the error, the degree of freedom is AB times n minus 1. So we have 2 times 2 times 2 replicates minus 1 is 2. We get 4. Degrees of freedom 4. And these were all the values we calculated. So the mean square is the sum of squares divided by the degrees of freedom. Here we get 2 over 1 is 2, 242 over 1 is 242, 1,152 is divided by 1 is 1,152, and 6 divided by 4 is 1.5. We take our error and we use it to calculate our F value. We take our mean square value for each, and we get F values. For factor A, it's 1.33. For factor B, it's 161.3. And for the interaction, it's 768. So I think the hardest thing here was calculating the sum of squares. Again, we don't have to do that, but we have to do this part. You have to understand how we're getting these F values and how we're calculating these degrees of freedom to get the mean squares. So with these values, do we have a problem or do we not have a problem? Well, we're going to be looking at the F value. We're going to be looking here at the 95%, so F is alpha equals 0.5. And remember V1 and V2, where this would be for the numerator, and V2 would be for the denominator. So here, we're going to have an F value, 0.05 for numerator, has a value of 1, and degrees of freedom of 1. The denominator has degrees of freedom 4. And this is actually the same for all of these. All of these have a numerator of degree of freedom equal to 1, and the denominator is equal to 4. So we go to our F table. Here we have the V1 is always equal to 1, and V2, or FAL2, is equal to 4. So we see for all of our cases, our critical F value is equal to 7.71. And again, what were we trying to do? We were trying to see if our F observed is greater than F critical, which is in this case 7.71. And if yes, then reject the null hypothesis. And again, the null hypothesis was that there was no difference. They're not significant. So what do we find out? Well, the F value was 1.33 for factor A. The critical value is 7.71. Is 1.33 greater than 7.71? No. Factor A is not significant. Factor B, we get 161.3. Is that greater than 7.71? Yes, factor B is significant. For the interaction, 768 versus 7.71. Is that greater? Yes. This means, though, that the interaction is significant. It means that we see an effect that's greater than the random error to a 95% level. So we say the interaction was significant. And the idea there is that nice that factor B was significant, but actually, because of this interaction, we can't really use this. We can't use the effect that we've calculated. And we had this before. Do you remember this? When we looked at this graphically, we saw that these lines crossed. We saw that when one factor was varied in one direction from low to high, the other factor would vary in a certain direction. When one factor was at a certain level, the other factor was varied, we would see a variation in one direction. But when the factor was moved to a different level and we varied the other factor, the variation was in the opposite direction. We saw this with the graphs crossing if you went through those exercises. And so once we see that this interaction is significant, then we cannot use our effects. So this is why it's important then to do these, to finish the DOE. You're checking for the significance of factor A and factor B, that's good, but you're also checking to see if the interaction is effective. And so in this case, unfortunately, we cannot use our lawnmower example. We have to maybe go back and design our experiment a little more differently with different factors so that we can then draw some useful conclusions for our lawnmower design. Okay, thank you.